This is the magic function that if you measure in that coordinate system, everything is linear. And it's simple, e to the minus 1 over x, obviously. If you measure the system in these coordinates, ddt of that function is just lambda times that function. Okay? So this is what my wife calls the Feynman method of solution. You scratch your head and you write down the answer. Okay? But this doesn't work for more complex systems. You're not going to write down the magic eigenfunctions for turbulence. Okay? And I'm actually quite convinced that he had thought about this exact problem before, now that I've thought about it. So this is now a homework problem in my intro math class. What you do, sorry, this is the wrong slide. My apologies. I'll show you how to derive this. It's a homework problem in my intro math class. I'll show you in just a minute, okay? But I want to take a step back. So the Koopman operator theory, we've already seen kind of the Poincare geometric view of dynamics. This is how we computed the finite time Lyapunov exponent. We followed trajectories. That's what we've been doing for 100 years, is follow trajectories and find manifolds. But there's this new kind of operator theory that's working, instead of on trajectories of x, it's operating on measurement functions of the state g. G is a function. It's not a trajectory, it's an abstract function in a Hilbert space. It has an infinite dimensional representation. And in that representation, the Koopman operator linearly advances those measurement functions forward in time. So if I have a measurement g of my system at time k, if I hit it with this linear Koopman operator, it advances me to the next time step, okay? And what I showed you in those simple numerical, those simple 2x2 and 3x3 examples, is that what I want to do is find something called a Koopman invariant subspace. I don't want to work in an infinite dimensional function space. I want to have 3 observables where if I measured my system in those 3 observables, I get a closed 3x3 linear system for how they evolve. Those are defined by these invariant subspaces, so that if G is a combination of M observables and I hit it with Koopman, it's still in the span of those M observables. That would give me an M by M matrix that would evolve my system linearly forward in time. Okay, and so that's what we're trying to do in this is nonlinear system identification. We're trying to find those invariant subspaces. We're trying to find these functions that when I observe my system in those functions, they behave linearly in time. Okay, so here's where I'm going to show you how you find the solution of x dot equals x squared. So we had our original dynamics x dot equals f of x. We're trying to find these special magical coordinates phi of x so that they behave linearly in time. Yeah? And these phis are eigenfunctions of the Koopman operator, and the lambda are eigenvalues. So that's what the coordinate transformation means. These are just an eigendecomposition of the Koopman operator. And so what I can do is I can apply the chain rule to this quantity here. So I can get the grad of phi of x dotted with x dot, which is grad phi dotted with f of x. That's what the time derivative of phi of x equals. And that has to equal lambda phi of x. Okay? This is a partial differential equation for Koopman eigenfunctions. It's a really ugly PDE. I've shown this to my friends who specialize, whose careers are solving PDEs, and they tell me it's very nasty and hard to solve. Okay, but at least in 1-dimension and 2-dimensional dynamical systems, you can actually analytically solve for the Koopman eigenfunctions. Okay, pretty sure that's what Clancy did. I'm assuming. I'll ask him next time I see him. If you take this differential equation, what you can do is you can assume that phi of x has an expansion, a power series. Actually, you need to assume it has a 2-sided power series, a Laurent series. So it is a sum of positive integer powers of x and negative integer powers of x. And you take that Laurent series and you plug it into this PDE and you solve for all the coefficients like you do. This is how Bessel's functions were derived. And what you get out is the power series expansion, the Laurent series for e to the minus 1 over x. You can solve for the series representation of the solution of this eigenfunction for simple PDEs. Okay? Any questions? That's a lot to digest. Yes?
So if you look at the Liouville equation,
yes.
So the Liouville equation would be partial t plus f nabla p.
Yeah.
And so this is the eigenequation of the Liouville equation.
Yeah, so this is absolutely right. This is the eigenequation of the Liouville equation, which is the continuous time analog of the Perron-Frobenius equation, which is the dual of the Koopman operator. These are essentially all cousins. It's a big family of operators. And the idea is that you can take your nonlinear dynamical system, and if you think about how probability densities of trajectories evolve through that system, or how measurement functions of that system evolve, those can be seen as linear dynamical systems, but in an infinite dimensional space. Again, I can't tell you about all of this in an hour, but the keywords are Koopman, Perron-Frobenius, and Liouville. Okay, if you like Google those, you'll find this rich connection between all of those different theories. And so in practice, what we do is we try to approximate these functions phi as some expansion in a basis. You pick a basis, you measure a lot of data, you do a regression that's basically a DMD regression, but onto nonlinear functions of the state, and you try to approximate these eigenfunctions doing that. And that's what this extended dynamic mode decomposition does from Williams, Kevrikides, and Rowley. So they were the first, at least in the Koopman context, to show kind of how you would get these nonlinear eigenfunctions from data in a dynamic mode decomposition framework. Now it turns out, and they applied it to some cool systems like this Duffing one that we worked on earlier. Okay, it turns out that in the chemical kinetics community, they actually discovered this about 3 years earlier, which I find really interesting. So I think it was Kloos and Noe and others developed this for molecular dynamics also in parallel. And so there's kind of two groups of people developing this, and we should try to learn from the molecular dynamics people because they're about 3 years ahead. Okay, so this is your PDE for eigenfunctions.
We have a question.
Oh, another question, yeah.
It's not a naive question, but it is perturbing me a little. In order to have these modes, you can ask yourself first, do they exist? I mean,
they have to exist.
Do Koopman operator do have eigenvalues? And it turns out that if you take for topology for Hilbert space, the Hilbert space L2, for instance, then the spectrum of the Koopman operator is continuous, and there is no eigenvalue. So how to get these eigenvalues, knowing that the Koopman operator has purely continuous spectrum? Or, another way to put it, can you change the Hilbert space in order to get eigenvalues? Sorry.
Yeah, so it's a really good question. This is not an intro question, and I would like to translate this question a little bit for those of you who might not have followed that entirely. Okay, so I said that there is this Koopman operator, and it works in this Hilbert space. You should be thinking, well, what's your inner product? What is your Hilbert space? Which space of functions are we talking about? And it makes a huge difference to whether or not these things are or are not amenable to, solving for these eigenfunctions and representing them is the choice of Hilbert space. That's a very technical consideration. Lots of people are working on that. It's not something that I work on, but I know that lots of people are thinking about alternative Hilbert spaces. So Dimitri Giannakis and Andrew Stewart and Krithika Manohar are all working on this. The second part of your question, there's something called a continuous spectrum. How many of you have heard of a continuous spectrum before? It's a really interesting and messy concept. It's actually closely related to chaos and mixing from the last lecture. And I'll tell you a little history. This will be a little bit of a diversion. So I was sitting in a workshop on Koopman operator theory at United Technologies 5 years ago. everyone is excited about this. There was about to be, millions of dollars of grant funding to study Koopman theory. And, we're in this room, everyone's talking about their latest and greatest technology. And I asked the question, how do you use this to solve the pendulum? Because if I can't do Koopman operator theory on my simplest textbook example of a pendulum, no one's going to use it, okay? And it turns out I didn't know about continuous spectrum 5 years ago, and this is the simplest system you can think of that has a continuous eigenvalue spectrum. So what it means is literally, if I have my pendulum and it's in the down position and it's linearized, it has a pair of eigenvalues, plus and minus I omega. It has one distinct frequency, natural frequency. But as you slowly increase energy of the system, that frequency gets lower and lower. The period gets longer and longer, until eventually, when it's in the up position, it has an infinite period, so to speak, right? It would take forever to get back up to the top, which means it has zero frequency. So if you look at the complex plane, and my original eigenvalues were plus or minus I omega, if I look at the nonlinear pendulum, it has every eigenvalue between them. That's a continuous spectrum of eigenvalues. And that's one of the Achilles heels of Koopman operator theory. It is very, very hard to find a discrete representation for any system that has a continuous spectrum. We're still trying to figure this out. And if I can get to time delays, it turns out the time delays are how you handle this in practice. Yes?
Speculate. So this is the eigenequation of the Liouville equation.
When Bernd speculates, great things happen.
So the Liouville equation essentially is on L2. So the phi are normalized so that the integrals over the phi in the whole space is unity. And if something is L2, it should have a discrete spectrum. So a countable infinity, but discrete spectrum. So this would be my best guess for this spectrum.
This certainly sounds reasonable. I'll admit I am a practitioner. I like collecting data and doing regressions, okay? There are lots of technical issues here of finding the right inner product, finding the right coordinate system to find discrete spectrum. You want a discrete spectrum because when your eigenvalues are discrete, they have their own eigenfunctions that are these special measurement functions that you can work with, okay? So a lot of what you do here to approximate these things is you assume that your phi of x can be expanded in some basis theta. So you have some basis of functions theta, and you're going to say that your eigenfunction is some linear combination of those basis functions. Maybe these are Bessel functions, maybe they're trigonometric polynomials, whatever basis you like, okay? And we're just going to expand it out. And essentially what you can do is you can build a data matrix of theta evaluated on trajectories. And you can build this gamma matrix that's basically all of this stuff on the left-hand side. It's just grad theta dotted with my dynamics. This is also a data matrix you can literally build from data, just like in DMD. This is basically x and x prime, okay? And now what you're going to try to do is this linear regression to find the eigenvectors of, theta dagger, theta prime in discrete time, or gamma dagger theta, theta dagger gamma in continuous time. And this is exactly what the extended DMD algorithm and this VAC algorithm, and it was Noe and Niske, they were the ones who discovered this in 2013 for chemical kinetics. Okay, so it's basically a DMD regression, but you're expanding your eigenfunction in some nonlinear basis. So you're augmenting with nonlinear measurements and doing that regression. Okay, that's what the extended DMD is doing. Okay, great. Any other questions about this? Yeah, in the back.
So you mentioned that we can take a basis and then find the coefficients for that basis and get the function phi. So I was thinking if we had taken that basis to get the Koopman operator in that basis, would we get like a low rank Koopman operator?
Yeah, so basically if I just pick a few of these lambdas and x's, that's model reduction. I can pick some subset of my eigenvalues and eigenfunctions, and that is a lower dimensional representation that is itself linear and captures some features of my original system. Yeah. So actually a great example of that, this reminds me, a good example of a continuous spectrum system like the pendulum or the Duffing example or lots of other systems, those systems have a Hamiltonian, right? The pendulum has a total energy that's conserved if there's no friction. Any conserved quantity is a Koopman eigenfunction with eigenvalue 0, because ddt of energy equals 0 times energy. Okay, and so that's actually a very useful Koopman coordinate system where all of the conserved quantities of your system are eigenfunctions with 0 lambda. They're in the null space of this operator. So that's very, very useful. And Ulrike Kaiser has written a beautiful paper showing that you can use that for control. Okay, good. Okay, I'm going to talk more about dynamical systems. I got 5 more minutes, and we're going to talk more about dynamical systems. And I'm just going to keep talking until I can't talk anymore. So this lecture is about system identification, but if you want, grant money, you call it model discovery. So it sounds so much more exciting to discover a model than to identify a system. So again, I would just highlight that system identification has been around for decades and decades and decades, 70 years of active research, tens of thousands of good papers. This is a tiny, tiny, tiny fraction of some of the modern papers that use machine learning for system identification. And what I'm highlighting in pink here is this recent trend to discover models that are so-called parsimonious. And parsimonious is just a fancy word for greedy. And what do I mean by greedy? Remember, we're always balancing accuracy and efficiency. Okay, and what I want are the models that are as simple as possible, but no simpler, or as complex as they need to be, but no more complex. Does that make sense? That's what we want. That's a parsimonious model. And oftentimes we're going to achieve parsimony by sparsity. That means we want as few terms in the model as possible, usually. Okay, so I'm going to tell you this is now kind of active work in my lab, but lots of other people are working on this too now. So I'm going to tell you about the sparse identification of nonlinear dynamics. We call it SINDY. How many of you have heard of this? How many have not? Oh, that's my favorite thing to see. Good, so I'll tell you about SINDY on the Lorentz example, and then I'll probably tell you a little bit more about this tomorrow applied to fluid systems. Okay. So remember, this is the Lorentz equation that has chaos, and it's a model for Rayleigh-Benard convection. And so it's a 3-state ODE. And if you look at it, it is nonlinear, but it's actually it's surprisingly simple. For how complex the dynamics are, the equations are relatively simple. There are only a few terms in each equation, and there's only a couple of truly nonlinear terms. There's an xy and an xz. Okay? And so the idea here is we want to, let's say that you didn't know what these equations were, and you wanted to discover, so now we're back to model discovery, discovering f of x, okay? We want to discover this right-hand side, but all we have are measurements of x, y, and z in time, and measurements of the derivative in time. Okay, that's the system identification problem. I measure time series of my data, and maybe I can compute derivatives, and that's all I have. So what would the dynamic mode decomposition give us in this example? So it would give me a 3x3 matrix right here, and it would be the absolute best fit linear operator that could possibly map x, y, and z into x dot, y dot, and z dot. How many of you think that you're going to capture the Lorentz dynamics with the 3x3 linear matrix? You can't, right? This has multiple fixed points and unstable periodic orbits. It's fundamentally nonlinear. And if we measure x, y, and z, there is no linear model in x, y, and z that can capture these dynamics. So kind of building on this idea, though, of doing a linear regression on data, what we're going to do is we're going to augment the right-hand side of this library to include nonlinear functions of our state, similar to what we did when we were trying to find Koopman operator eigenfunctions. We're going to assume that there's some some space of functions theta, and we're going to assume that my right-hand dynamics can be written as a linear combination of columns of theta. So instead of just x, y, and z, I can build x squared, xy, y squared, all the way up to z to the fifth. And these columns can be evaluated from data. These can be built just from the data I have here. I can take x and y and z, and I can compute x squared and xy and y squared and things like that. Okay? And so here's the key observation. We expect that almost every nonlinear dynamical system we've ever seen has been sparse. Open a textbook and find me a dynamical system that's not sparse. I challenge you, that's homework, okay? This is somehow sparse in the space of all the right-hand side functions that this could have been. This one's quite simple, and there's only a few terms. That's what I mean by sparse. So now what we're trying to find, this is the coefficient matrix that if you multiplied theta, you would get x dot. This is like the truth that I know. We're going to try to find the fewest columns of theta that add up to explain x dot, and the fewest columns that add up to explain y dot, and the fewest columns that add up to equal z dot. And that's a sparse regression problem. When I say fewest, that means we're going to have a sparsity penalty on our regression. We're going to do the same least squares regression, but we're going to add a sparsity penalty. Okay? And so when you do this sparse regression, and 20 years ago, this would have been a combinatorially hard problem. 20 years ago, to find the sparsest column, set of columns that add up to x dot would mean you would have to try all sets of 2 columns, and then all sets of 3 columns, and then all sets of 4 columns until it worked. And that would be a combinatorially n choose p hard problem. That would be an NP hard problem. And only in recent years, in the last 10 or 20 years, have techniques from statistics and applied math allowed us to reliably solve this sparse regression problem in a convex optimization that scales to large problems. Okay, so really we're relying on statistics that came out of Stanford 20 years ago. Okay, and now it's like it's like a library on GitHub or in Python. Okay, so we find the sparsest, the fewest columns of theta that add up to equal x dot, and what comes out are an x term and a y term. That's what lights up when you do this regression. And lo and behold, that was what was in the x dot equation. You do the same sparse regression on the y dot equations, and you find that the fewest terms needed to explain that are y, x, and xz, which again were the terms in the original dynamics. We didn't give it the equations. All we gave it was data, and we're discovering what those equations are. Okay, you can do this in Z. And so what you get when you do this sparse regression, when you assume that your answer has to be simple, you actually discover the structure and the parameters of your original nonlinear dynamical system. This is nonlinear system identification. Remember I told you in your dynamical system you want models that are interpretable and generalizable? These models are interpretable because there's only a few terms, and they're the terms that were actually in the model. They tend to be generalizable because you don't overfit as much when you penalize fitting all of your parameters. Okay? Would anyone like to ask any questions about this? Yeah.
In the matrix that you have below, all the gray columns that are not being used,
Yeah.
is it like waste of computation work, or do we really need them? I mean,
Oh, so those are candidate terms that could have described the nonlinear dynamics, and we don't know what the dynamics are. So we have to build theta to have lots of possibilities, and then the sparse regression selects which terms were active in the dynamics. So when our final model, everything else gets zeroed out, and we only compute the things in color here. So the final model is very efficient because there's only 7 terms being computed.
okay, thank you.
Yep. Okay, I'm going to keep going on. So I assumed that I had access to X, Y, and Z and their derivatives. That's usually a lot to assume in system ID. You usually don't have derivatives. So what we showed, kind of the first thing we showed as a proof of concept when we developed this, was could you work on noisy measurements of your state only? So if you had X, Y, and Z and they were noisy, so this kind of fuzzy attractor, you can compute these regularized derivatives, these total variation. And if you haven't heard of total variation, please Google it. It is amazing. It'll change your life if you have noisy data, okay? This was developed in the 80s for image cleaning. Okay, and it's like 10,000 citation paper. The derivative version of it is really useful for noisy time series data. And if you had this noisy data and computed these approximate derivatives and plugged those into this algorithm, you still obtain the right structural form of the equation. All of the terms are actually quite accurate except for this term here, which is off by about 20%. And I can't tell you why. But it doesn't matter that much, obviously, because you still get the right attractor. Okay, good. So you can discover nonlinear dynamical systems kind of in the same spirit of what we're doing in DMD and eDMD, but now you can use it to discover the actual vector field F itself.